Now let's move to the outer solar system and look at the most geologically active small object in the solar system. Saturn's moon Enceladus is much smaller than the Earth's moon, yet it nicely illustrates how an icy composition and ongoing heating can make a world active, even if it's so small that it should have cooled down long ago.
One of the key ideas we keep coming back to is that larger worlds stay hot longer, and it's this internal heat that powers active geology. This is why the Earth and Venus are geologically active, while the Moon is long dead, and Mars has only minimal activity. But an important question to keep in mind is, just how hot does a world have to be geologically active? In fact, the interior has to be hot enough that it can flow, meaning that it's near the melting point. However, remember that the melting point of a planet's interior will depend on what it's made of. For worlds like the Earth and its moon, the mantle is made of rock, so the interior has to be nearly hot enough to melt rock. But what if the interior is made of something else?
In the outer solar system, one of the major building materials for moons is ice. This is usually water ice, but it can include things like frozen ammonia, nitrogen, or methane. From their densities, we find that these moons can be made of 10 to 100% ice, with 50% being fairly typical.
The other important feature of the Jovian moon systems is that they're often kept unusually warm through tidal heating. When two or more moons tug on each other, they make their orbit slightly eccentric, meaning that the orbit is not quite circular. This is especially common when the moons are in a resonance, which means that the orbit period of the inner one is a simple fraction of the orbit period of the outer one, such as 1/2 or 2/3. When a moon's orbit isn't circular, the strength of the tidal pull from the planet changes, and this causes the size of the tidal bulge on the moon to change. In effect, the moon's shape flexes back and forth each orbit as it moves closer and further from the planet. If the planet is a large Jovian world, then the tidal force is very strong, and even small changes in distance cause big changes in the moon's tidal bulge. It's the friction of this tidal flexing that releases a lot of heat.
The combination of icy composition and tidal heating mean that many fairly small moons in the outer solar system are very geologically active. This activity usually takes the form of tectonics, especially parallel ridges and valleys produced as tides alternately squeeze and stretch the surface, and ice volcanism as underground water emerges onto the surface. We see examples of geologic activity on several moons, including Neptune's Triton with its nitrogen geysers and water ice volcanoes, Jupiter's Europa with its very smooth icy surface covered in long cracks, Uranus's Miranda with its parallel ridges, and Saturn's Titan with its thick atmosphere and lakes of liquid ethane.
As we look at Enceladus, it seems in many ways just another small, icy moon of Saturn. Its mass is only 10 to the 20th kilograms, 50,000 times smaller than the Earth, and its diameter is 500 kilometers, similar to the state of Arizona. It has a density of just over 1.6 grams per cubic centimeter. This is a little higher than average for Saturn's moons, but not a lot higher. It suggests a composition that's about 60% ices and 40% rock and metal. However, there are a few things that make Enceladus very unusual. First, it reflects over 90% of the sunlight hitting it, giving it a surface that's brighter than freshly fallen snow. This is one of the most reflective objects in the solar system, and it suggests an exceptionally young surface. Enceladus also has regions with almost no impact craters. It's the smallest moon in the solar system to have so much of its surface cleared of most craters. Perhaps most unusually, Enceladus is embedded right in one of Saturn's rings, the E-ring, which appears to be made up of fine ice crystals in a hazy band. In this picture of the E-ring, Enceladus is the dark spot right in the midst of the ring. It looks like the material in the E-ring may even be emerging from Enceladus.
So Enceladus appears to be the smallest active moon in the solar system, especially around its south polar region. The activity appears to be centered around a series of long cracks in the surface, known as the tiger stripes. This enhanced color image shows that the ice around the tiger stripes has a different texture than the surrounding ice. This texture does not survive very long under solar radiation. Within about 10 years, it would be converted to ice with a different crystal structure. The fact that we see it here tells us that this ice is being actively produced today. When we look at the thermal radiation produced on this part of Enceladus, we measure temperatures of up to 190 K. This is still well below the melting point of water ice, but it's much warmer than the less than 100 K temperature of the surrounding surface. Finally, there's a thin atmosphere of oxygen above the South Pole. This appears to be produced by the breakup of water molecules by sunlight. Something is lofting enough water above the surface of Enceladus to allow the formation of this atmosphere.
In 2006, the Cassini spacecraft took the first pictures of a volcanic eruption in this backlit view of Enceladus. This was the first ice volcano caught in the act of erupting. Both gas and ice crystals were seen erupting from the tiger stripes. The ice crystals were tiny, just 10 to the minus 6 meters across. This is 100 times smaller than the thickness of a human hair. Since then, many more eruptions have been seen, such as this set of several tiger stripes erupting at once. Models of the eruptions suggest that there's an underground ocean being squeezed by tides, causing it to burst out through these weak points in the crust.
It's important to ask why this particular moon is the smallest very active moon in the solar system. There are other moons around this size that are much less active, such as Saturn's moon Mimas, shown here. So what's special about Enceladus? First of all, tidal heating is probably not enough to make Enceladus active. It's small enough that tides by themselves shouldn't be able to melt the ice. However, Enceladus does have a higher density than the other Saturn moons in its size range, so that means it probably has a larger fraction of rock than many of them. Remember that rocky material is where we find radioactive elements like uranium, so it's quite possible that Enceladus has a little more radioactive heating than its neighbors. This radioactive heating also isn't enough to make Enceladus active, but it can provide enough heating to soften the ices in the mantle. Then tidal heating can cause those softer ices to start moving around, causing enough friction to power active ice volcanism. Enceladus is the extreme case of a small, active, icy moon. But the same combination of tidal heat and icy composition is important for many outer solar system moons.